I'm Tammy Kolda, an applied mathematician, and this is Unlocking LaTeX Graphics. On this channel, I present tutorials on using TikZ and PGFPLOTS. The videos on this channel are based on my book, Unlocking LaTeX Graphics, as well as some bonus materials. Today, I'm going to show you how to draw slope fields in LaTeX using pure TikZ. A slope field is a way to visualize a differential equation. This was a request from a viewer, and it's a great challenge. In fact, this is just part one of a multi-part series. Today, we'll draw a slope field with basic TikZ. In follow-up videos, I'll build up the skills to do this in PGFPLOTS, which is a more powerful approach that can handle more complex functions and larger numbers. If you've taken a differential equations course, you've probably seen slope fields. They're a way to visualize a differential equation by drawing short line segments that show the slope at each point on a grid. In this video, I'll show you how to draw axes manually in TikZ, how to use nested foreach loops to draw normalized slope field lines, and how to swap in different differential equations. I'll show you one equation where TikZ fails, tune back in for the PGFPLOTS fix for that one. And I'll show you another slope field where we have special handling for vertical slopes. So let's get started. Before we jump into the code, let me briefly explain what a slope field is. A slope field is a way to visualize a differential equation of the form dy dx equals f of xy. I use the shorthand y dot to denote dy dx. At each point xy, we draw a short line segment whose slope is f of xy. This gives you a global picture of how solutions to that differential equation behave. If you were to place a solution curve on this picture, it would follow the directions of these line segments. The example here shows the slope field for y dot equals x minus y, which is the equation we'll code up first today. Let's zoom in on what's happening at a single point. At each grid point xy, we draw a line segment of a fixed length, which I'm calling len. And the slope of that segment is f of xy. Now let's build this in TikZ. Before we get started, let's set up our document. I'm using the geometry package to set 1-inch margins. The Parscape package avoids paragraph indentation, and HyperRef lets me link the author name to the YouTube channel. The key package is TikZ. That's all we need for this approach today. Let's start by drawing the axes for our slope field. First, I define 3 variables using PGFMath set macro. The variables dmin and dmax set the range of our axes. These have to be integers for the rest of the code to work. I'm using -6 to 6. The variable len is 0.35, which controls the length of the slope field lines. I open a TikZ picture environment and draw the x and y axes using draw with an arrow tip. The axes extend from dmin minus 0.4 to dmax plus 0.4. This gives a little extra room beyond the tick marks. I also add axes labels and name the y-axis label node so I can reference it later when I add the title. Now let's add tick marks to the axes. I use a foreach loop to draw small lines at each integer from -6 to 6 on both axes, with labels below for the x-axis and to the left for the y-axis. Observe that I'm using an inline foreach loop inside the draw command with the contents of the loop itself inside curly braces. Now, there's a weirdly annoying thing about TikZ. Observe that the lower ticks are -6.0 on both the x and y axis rather than just -6. I can fix this by adding int around the definition of dmin, which I'll do here. And now when I recompile, everything is fine. This is one of the many oddities of TikZ. There are also little zero labels that we probably don't want because they're a little bit awkward based on their location. But I'm not going to worry about that because it'll be covered up by the slope field lines anyways. Moreover, future episodes will show how to do this with PGFPLOTS, which doesn't have these issues. Now for the heart of the drawing, the double loop that creates the slope field. I first define dmin b as dmin plus 0.5. This gives me a step size of 0.5 for my grid on which I'm going to be drawing my slope lines. I have to calculate this dmin plus 0.5 in advance. I cannot do that calculation inline inside my loop. Then I have two nested loops. The outer loop goes over x values and the inner loop goes over y values, both stepping from dmin to dmax or -6 to 6 in increments of 0.5. There's 25 values in each direction, so 625 lines total. Inside the loop, I compute the slope at x minus y. In other words, m is my f of x, y value. So this is the differential equation, y dot equals x minus y. Then comes the normalization. Let me pop up the slide to explain the math, and then we'll come back here. Here's one of our line segments centered at the point x, y. We need to figure out how to compute the endpoints. There's lots of different ways you could do this. If we think of this segment as the hypotenuse of a right triangle, the horizontal side is proportional to 1, and the vertical side is proportional to f of xy. By the Pythagorean theorem, the hypotenuse is just proportional to the square root of 1 plus f of xy squared. We want the total length of this segment to equal len. Now we're drawing from the center outward in both directions, so we only need half the length on each side. I'll call the horizontal half distance dx and the vertical half distance dy. Since the full hypotenuse is proportional to the square root of 1 plus f of xy squared, and we want half the length to be len over 2, we get dx equals len over 2 divided by the square root of 1 plus f of xy squared. And dy is just f of xy times dx immediately. So the endpoints of our segment are x minus dx, y minus dy, and then the other end is x plus dx, y plus dy. And that's exactly what this code here does. We compute our dx and we compute our dy, and then we draw our line segment from x minus dx, y minus dy to x plus dx, y plus dy. Each line segment will be centered on its grid point. I compile and you now see the slope field. Notice in the line B, line y equals x. The lines are horizontal because the slope x minus y is 0 there. Let's add a title to the plot. I add a title using a node positioned above the y-label node. If I recompile, you can see that that title is at the top. Now for the fun part. The beauty of this approach is that we can change the function by editing a single line of code and get a completely different slope field. Let me try it. F of xy equals sine of x plus y. Remember that TikZ trig functions expect degrees, so I use DEG to convert from radius. When I compile that, you can see the oscillatory behavior from the sine term combined with the growth from the y term. Now let's try f of xy equals sine of x times y. This creates a really interesting pattern with waves that change frequency depending on where you are in the plane. What about f of xy equals e to the power of x minus y? When I compile this, we actually get an error. As you can see, this one doesn't work. We get an error that the dimension is too large. This is a limitation of the PGFMap library. When the exponent gets large, the numbers overflow and TikZ can't handle them. This is one reason you might want to use PGFPLOTS instead, which I'll cover in a future video. Let me show you one more function that demonstrates a trick for handling vertical slopes. So I'm going to replace m dx and dy in this example. Here, f of xy is 2 cosine of x divided by y. When y is 0, we get an nan or an in, depending on how you want to define it, and that causes problems. The hack is to use if then else. When y is close to 0, I explicitly set dx to 0, and I explicitly set dy to len divided by 2, which makes a vertical line segment. Otherwise, I compute the slope normally. The same if then else trick handles the function definition, where I substitute 1 for y when it's close to 0 to avoid the division error. The result of that calculation doesn't matter because we override dx and dy. When I compile this, you can see the vertical arrows along the x-axis where y equals 0, which is exactly what we expect since the slope is infinite there. I hope you enjoyed today's episode on drawing slope field using TikZ. We covered how to draw axes manually, how to use nested for each loops with normalized line lengths, and how to swap in different differential equations. In a future video, I'll show you how to do this using PGFPLOTS through a combination of tables that we'll build up and something called a quiver plot. Stay tuned for that. I include a link to the overview document I created today and the show notes. If you found this helpful or interesting, please click like or subscribe. If you have TikZ or PGFplot questions, please post them in the comments. If you want to learn more, please check out the other videos. I also have a book, Unlocking LaTeX Graphics, available for purchase at major book retailers. Thanks for watching, and thanks to Nick Pettit for today's topic.